Hello, everyone, and welcome back, Math Detectives. I am so thrilled to have you here for another fantastic geometry lesson. Today, we're putting on our detective hats and jumping into an explainer all about angles. We're going to use some ironclad rules of math to solve some truly fascinating mysteries hidden inside intersecting lines. And, we might even catch a few sneaky textbook mistakes along the way. Okay, let's dive into this. Here is our syllabus that'll guide our investigation today. First, what are opposite angles? Second, solving unknown angle mysteries. Third, the reflex angle trap. And fourth, a quick revision and wrap-up. Section 1. What are opposite angles? Consider this our official detective briefing on the 2 golden rules of our geometric universe. So, golden rule number 1. Whenever 2 straight lines cross, they naturally create 4 separate angles around that center point, right? Well, the angles that sit directly across from one another are known as vertically opposite angles. And here's the absolute magic part of this rule. They are always equal. Literally always. So if one of those angles is 120 degrees, its vertically opposite partner, right across from it, is also exactly 120 degrees. This rule is incredibly reliable. It's our very first key detective tool. Now, take a look at this single powerful number, 180 degrees. This brings us to golden rule number 2. The sum of the angles on any straight line always adds up to exactly 180 degrees. So let's think back to that intersection we just looked at with the 120-degree angle. How do we find the angle sitting right next to it? Well, it's just simple deduction. Since a straight line is 180 degrees total, we just take 180, subtract that known 120 degrees, and boom, we're left with 60 degrees. Armed with just these 2 tools, we can figure out literally every single angle at any basic intersection. Section 2. Solving unknown angle mysteries. All right, the briefing is over. It's time for the field work. We're going to apply these golden rules to an actual, complex-looking problem to see just how powerful they really are. Here's practice question 1. We're looking at an intersection made of straight lines AB, CD, and EF. We know 3 of the angles, 56 degrees top left, 60 degrees on the right, and 64 degrees bottom left. But we need to find the 3 unknown angles, P, Q, and R. Now I know, taking a first glance at this, it probably looks totally overwhelming. I mean, lines and numbers crisscrossing everywhere, but don't panic. By isolating this web and breaking it down strictly line by line, we are going to crack this case wide open. Let's move to and see how this builds. First, let's just focus our complete attention on straight line EF. Just ignore every other line for a second. Because EF is a straight line, we know all the individual angles sitting along it have to add up to 180 degrees, right? So we set up a simple equation. The 56 degrees we know, plus our unknown P, plus the 60 degrees equals 180. Add 56 and 60 together, you get 116. Subtract that 116 from 180, and there it is. P is exactly 64 degrees. First mystery solved. Moving right along, let's shift our gaze to the straight line AB. We're going to treat this just like a giant puzzle, smoothly slotting in the pieces we already have. The angles resting on line AB are the 56 degrees at the top, our unknown Q, and the 64 degrees we were given at the bottom left. Together, they have to equal 180 degrees. So 56 plus 64 gives us a clean 120. Subtract that 120 from 180, and we find that our unknown Q is exactly 60 degrees. We are really on a roll now. Okay, let's bring it home and complete this first investigation by checking out straight line CD. The angles arrayed along this line are 64 degrees, our final unknown R, and 60 degrees. Following the exact same logic we've been using, 64 plus R plus 60 equals 180. Add the numbers up, you get 124 plus R equals 180. Subtracting 124 leaves us with R equaling 56 degrees. Just look at that. By staying calm and systematically applying one simple rule about straight lines, we successfully deduced all 3 unknowns. Angle P is 64, Q is 60, and R is 56. Truly brilliant work. Section 3, the reflex angle trap. Now, detectives, I need you to brace yourselves for a bit of a plot twist, because we're entering myth-busting territory. Sometimes the printed textbook itself is actually wrong. Before the real trickery starts, let's quickly look at practice question 2A. This one simply asks us to construct a basic 90-degree right angle, angle ABC. The reliable process here is one we all know. First, you draw a straight ray, BA. Then, carefully place the center of your protractor right on point B, aligning the 0-degree line straight along the ray you just drew. Mark a dot at the 90-degree line, and finally join point B to that mark, drawing ray BC. And there you have it, the whole shebang. A perfect standard 90-degree right angle. Easy enough, right? Now, what's really interesting about this slide is when we get to question 2b, which asks us to construct reflex angle EFG equals 180 degrees. Look closely at the fundamental contradiction here. A true reflex angle by strict mathematical definition has to be greater than 180 degrees and less than 360 degrees. An angle that is exactly 180 degrees, well, that's simply called a straight angle because it literally forms a straight line. It's definitely not a reflex angle. So as an observant math detective, you can confidently call this out. The textbook made a printing mistake. If they truly want 180 degrees, you just draw a straight line and move on. Next up, let's look at practice question 3a. Here we're asked to draw a true reflex angle of 305 degrees. Now, because our standard protractors usually only measure up to 180 degrees, we have to use a clever little workaround. A full circle is 360 degrees. So we simply subtract our target angle of 305 from 360, leaving us with 55 degrees. That right there is our inner angle. You just use your protractor to draw a normal 55-degree angle, and that much larger angle wrapping around the outside, that's your perfect 305-degree reflex angle. It brilliantly illustrates how the smaller inner angle and the larger outer reflex angle physically complete a full 360-degree circle together. And that brings us to our final trap in question 3b, a prompt asking for reflex angle PQR equals 100 degrees. By now, your detective alarms should be ringing loudly. 100 degrees is absolutely not greater than 180, so it physically cannot be a reflex angle. Yep, you guessed it, another printing error. So how do you handle this on a real assignment? Well, you have two great options. Option A, you assume the authors just meant a normal angle, and you draw a standard 100-degree angle. Or, option B, you assume they truly wanted the reflex angle corresponding to 100 degrees, in which case you take 360, subtract 100, and draw a 260-degree reflex angle around the outside. Either way, you are completely in control of the math because you actually understand the underlying rules. Section 4, quick revision and wrap-up. Let's head into a quick debrief so we can lock all these concepts firmly in our memory. We have cracked some remarkably tough cases today and even outsmarted the textbook's printing errors. So the crucial point is this: complex geometric mysteries are solved with simple, reliable rules. When straight lines intersect, they automatically create vertically opposite angles. And remember, opposite angles are always equal to each other. Second, the sum of angles on any straight line is always exactly 180 degrees. By just trusting these basic rules and deliberately using them step by step, you can break down the most overwhelming diagrams into totally solvable, manageable equations.
And thanks for watching. Bye, students. Don't forget to subscribe for more math fun videos. See you in the next lesson.